Hello, in this video we're going to find an equation of the tangent plane to the given surface at the specified point. So the meaning of this is that this equation here represents a surface, or the graph of this equation is a surface. And I was sort of thinking about, well, should I try to sketch that graph? It's not one of these graphs that we learn about or that we're expected to really know. So I don't think we have to sketch that at all. I mean, it didn't ask us to do that. And then it gets to the point, well, should I try to sketch that? Just saying that it looks, you have this surface. And so that it's always hard, in my opinion, to sketch a graph anyway, even if you have a computer. So you have this surface. And one of the things is, like, say, if when x is equal to 1, you get z is the square root of y. So the plane x equals 1 gives the equation. All right. So if x equals 1, z is equal to the square root of y, and you could sketch that graph. We know what the square root of y graph looks, how it looks. But I just thought I would point that out, that there is a surface here, and I was just giving some idea of how you could sketch that surface. But then what we're doing is we're looking for a tangent plane, the equation of a tangent plane. And what's a tangent plane? A tangent plane is a plane that touches. Tangent the word has origins in Greek, and the Greek word tangents means touching. So we're looking for the equation of a plane that touches there. And so let me get then to the tangent plane formula that we have, that we learned about, supposedly. So z equals z0 plus f x 0 y0 plus, x minus x0 plus fy x0 y0 y minus y0. And okay, so I mean, there's different ways you can move these things around, but this right here is the partial derivative of f with respect to x evaluated x0 y0. And this one right here, I'm just writing in different notation, is the partial derivative of f with respect to y evaluate x0 y0. And keep in mind that z0 is given. So this point here is x0 y0 z0, this point right here. That's what this is. Okay, so z0 is 1 in this case, but just keep in mind that z0 is the same thing as is evaluating f at x0 y0. So for our problem here, for our specific problem, x0 is equal to 1, y0 is equal to 1, and z0 is equal to 1. And notice if you put x equals 1 and y equals 1 into this function, we get z is equal to 1. So what we're going to do is find the partial derivatives of the function evaluated x0, y0. And so these will be numbers. They'll be constant numbers. And we're going to find those. So I'm going to write then z equals fxy equals the square root of x times y. And I'm going to differentiate, but to do that, I'm going to express this as an exponent, or powers of x and y. Powers of x and y. And all right, so I have that. Now the partial derivative of f with respect to x is found by taking the derivative with respect to x and thinking of y as a constant. So x to 1/2 is a power of x, and we'll use the power rule. So I have 1/2 x to the minus 1/2 times y to the 1/2. And this simplifies as y to the 1/2, or 1/2 times y to the 1/2 divided by x to the 1/2. I don't really need to simplify it, but it just seems like, I don't know, it's just sitting right in front of me. Why don't I simplify it? And then fx evaluated at 1, 1, because those are our points for x and y, where we're finding the tangent line, is 1/2 square root of 1 divided by 1. So that's 1/2 square root of 1, which is equal to 1/2. Okay, so anyway, getting those. Maybe it's good. Some people say it's better to write vertically below, possibly. Okay, anyway, doing it that way. All right, then Fy xy is found by taking the derivative with respect to y, where we consider x as a constant. I mean, by symmetry, there's lots. We know that this is Fy11 is going to be a half also, but let's just work it out. So we have x to the 1/2, 1/2 y to the negative 1/2, and this will give 1/2 x to the 1/2 divided by y to the 1/2. So this is going to be 1/2 square root of x over y, and then okay, and so then Fy11 is equal to 1/2 square root of 1 divided by 1, which is equal to 1/2. All right, so we have all the ingredients for our, to make our cake or something or other, to plug into the formula. So we have all these ingredients, and we just plug it into this formula. So there we go. So let me try to put those all on the same screen, all at once. So z equals 1 plus 1/2 x minus 1 plus 1/2 y minus 1. I would say that the real challenge with this problem is finding the partial derivatives with respect to x and y. And I don't really think that was as challenging for this problem as it could have been, and as we might see in other problems. So maybe I'm just picking the easy one to do, but I thought it seemed like a good one to try out. All right, anyway. And we see that these constants here, the 1 minus 1/2 minus 1/2, all cancel to make 0. So we have z equals 1/2 x plus 1/2 y. And, okay, so the way the answer is given in the book is as follows. What the book does is it brings everything to one side, and so it's like that, except then they multiply through by 2. So this is one way to show a plane where it's one format, where you have a constant times x plus a constant times y plus a constant times z equals 0. That's one way to write the plane. This is a way to show the plane as a function of x and y. So I would say either one are actually just fine. Writing either of these is your answer. This one, gives us the normal line. But anyway, let's not get too much into that. Let's just answer the question. And sorry that the picture of my surface isn't so great, but I suspect if I were looking this up on a computer and trying to sketch the graph, it's not going to look that much better. But I will say it's going to look like, if you were to cut this on the side, it's going to look like this, I think. If I were going to do a cut of this, it's sort of like it's like a slice of, I don't know, I think about food sometimes when I draw these pictures. Oh, actually, the thing is that when I'm doing this, I'm sort of implying it's a solid, which it isn't. So anyway, yeah, so I have this surface. Just say there's a surface, and what we did is we found a tangent formula for the tangent plane of that surface. So that does that, and especially, the key is you have to know what the formula is and being able to take the partial derivatives and plug in. And so let me just point out that I highlighted so many things that it might not be clear what the answer is, but that's the answer right there. The final answer that's given in the back of the book. Okay, so I don't have anything else to say. Okay, thank you, bye.